In this problem, we're asked, is this series divergent or convergent? And this is the series, the sum from n equals 1 to infinity of 1 over square root of n plus square root of n plus n. So this question can be settled, this can be decided using a comparison test. So an is the term of the series that we're investigating. And what we want to do is to compare the behavior of an to the term from a known sequence, a sequence that we know it converges or diverges. And so our first task is to select the comparison series. And so what we do is we look for the dominant behavior of this term. So this is 1 over square root of n plus n. So as n gets larger and larger, the thing that's going to be dominating this behavior is the presence of the n term here. Square root of n is going to be far less than n in general. So we will compare an with the term dn, which is 1 over n, which is the term of a divergent series. It's the well-known harmonic series. Well, we're actually going to compare it to, it'll actually be a constant multiple of this term. But if the harmonic series is divergent, then so will a constant multiple of it be. Okay. So the way this goes is, so we're looking at an, which is a positive term. So there's no trouble between positive and, there's no complication with some terms being positive, some terms being negative. And what we can say is that, well, this is going to be greater than, well, most of the time strictly greater than 1 over n plus n. So we can replace the square root of n with n. In general, so this will hold for all n strictly bigger than 1. Okay, so the square root of n is always going to be less than n once n is an integer bigger than 1. And we've got a greater than here because we've taken this fraction and we've made the denominator bigger. So we've made the overall fraction smaller. And this is, of course, 1 over 2n. But the series sum of 1 over 2n, which you could write as half of the series 1 over n, is a known divergent series. So by the comparison test, the sum of 1 over root n plus n diverges also. Okay. So this was actually the standard comparison test working here, but you could also achieve the same outcome using the limit comparison test as well. And for doing that, using the comparison term 1 over n would be sufficient. So let's have a look at how that would work. So this is using the limit version of the comparison test. So here you take the limit as n goes to infinity of the term we're investigating, which I've called an, that's this 1 over root n plus n, and we'll divide it by the term dn. So this is where an is 1 over root n plus n, and dn is the term 1 over n. So this limit is going to be the limit as n goes to infinity of 1 over root n plus n, and when we divide by 1 over n, that's the same as multiplying by n. Now to determine the limit of this, okay, we want it's a quotient, so we want to use the kind of quotient rule of the algebra of limits theorem for sequences, but we can't do that yet because both the numerator and denominator are divergent. So the trick is to divide above and below by the highest power of n that you see, and the highest power of n here is n to the power of 1. So dividing above and below by n, we're going to have 1 over something plus 1. And this root n is, of course, n to the power of half. So when you divide it by n, we're going to have n to the negative a half, or 1 over the square root of n. It's dividing above and below by n. So now we can use the algebra of limits theorem because the numerator is a constant and the denominator term goes to 0 converges to 1, because this term 1 over root n converges to 0 as n goes to infinity. So this is 1 over the limit of 1 over root n plus 1, which in turn is 1 over the limit of 1 over root n plus 1. And so this is just going to be equal to 1, since the limit of 1 over root n as n goes to infinity is 0. So we have this limit equal to 1 here. This is the L that's talked about in the statement of the limit comparison test. And since this L was strictly bigger than 0, basically, then the limit comparison test says that the sum of the series an, which is the one we're investigating, it diverges also. So from n equals 1 to infinity. To draw the divergent conclusion using the limit comparison test, it's important that we have this, that the limit comes out as being strictly bigger than 0. But that's the case here.